Hi, previously we talked about the theory of acids and bases, and then we got into a very mathematical explanation of how acids behave, but we haven't really talked about how bases behave. In general, base equilibria behave very much like acid equilibria, but there are a few differences, and that's what we're going to talk about in this video. So let's first of all start off by looking at a generic base ionization reaction, which is slightly different than the acid ionization reaction. So here we have the base, and remember the base is going to react with a water molecule and snag a proton off the water molecule to form the protonated form of the base, or conjugate acid, and hydroxide. So let's now write an expression for the base ionization constant, which we are going to call Kb. Again, very analogous to Ka. You can see that the reactants always go in the denominator of the fraction. We have the original base down here. We don't put water in because it's a pure liquid. Then in the numerator of the fraction, we've got the two products, OH minus and BH plus. So again, this looks very similar to the Ka expression. Now let's talk about the equivalent to pKa, which is pKb. And pKb, like all p notation stuff, is the negative log of Kb. So for any Kb value you find, you can calculate the pKb just by taking that Kb value, in this case 6.7 times 10 to the minus 8th, taking the negative log of it, and in this case that gives us 7.17. And again, when you take the log of something, the sig fig rule is however many sig figs you had in the thing you took the log of, that's how many decimal places you put in your final answer. So now what we're going to talk about is a relationship between the pKa of an acid and the pKb of that acid's conjugate base. So for a generic acid, here's the acid dissociation reaction. The conjugate base of that acid is A minus. So now let's write a base reaction with that conjugate base, and we see that A minus is going to react with water to form the protonated form of the conjugate base, HA, plus OH minus. So here's the Ka expression for that acid reaction. Here's the Kb expression for that base reaction. And now what we're going to do is we're going to look at what happens if we multiply Ka times Kb. And so let's just plug in our expressions, and you'll notice something in these fractions. There are a couple things that will cancel out. We have Ha divided by Ha. We have A minus divided by A minus. And so Ka times Kb equals H plus times OH minus. What is the H plus concentration times the OH minus concentration? Where have we seen that before? Oh, that's just the value of Kw, the dissociation constant for water. So if Ka times Kb is Kw, let's try taking the negative log of both sides. And what we get is that pKa plus pKb equals pKw. pKw? Well, Kw is 10 to the minus 14th, so pKw is negative log of 10 to the minus 14th, which is just 14. So here's our relationship between the pKa of an acid and the pKb of its conjugate base. The pKa plus the pKb equals 14. Now we may not use this relationship for a while, but we will be using it when we get around to buffers, so just keep that in mind. Okay, so now we're going to dive in and do the sorts of calculations we did for acid, except we're going to make some tweaks. Because for base calculations, we're going to use the OH minus concentration, and a lot of times what you're going to get is pH or H plus, and so you're just going to have to convert to find the OH minus concentration or the H plus concentration using this relationship that we talked about previously. So when we talked about acids, I showed you how to calculate the Ka from a solution whose pH you know. Now we're going to do the same thing for Kb. So if you look at these steps, they're going to look very similar to what we used when we were finding the Ka from a solution with known pH. You start by making an ice table, and then there's this extra step. Use the relationship that pH plus pOH equals 14 to find the pOH, and then in step 3, we use that information to calculate the change in the OH minus concentration. So remember, when we did acid, we used the pH to calculate the change in the H plus concentration. So we've basically had to throw in an extra step there. So then the rest of the steps are exactly the same. You use the stoichiometric ratios to calculate the other concentration changes. You calculate the equilibrium concentrations and then calculate Kb from those concentrations. So here we have a solution of a base, a 0.10 molar solution of ethylamine, and we have a pH for it, 11.87. So we're going to start off by making an ice table, and as you can see, this looks slightly different, but not too different from the acid ice table, in that we have the concentration of the base, generic base. I mean, you could put the formula for the base, but I'm just going to use the generic table. The protonated base and the OH minus. The next step is to use pH plus pOH equals 14 to find the pOH. So we can rearrange that equation to get that pOH equals 14 minus pH. 14 minus our known value of 11.87 gives us a pOH value of 2.13. In step 3, we're going to use that value for pOH to calculate the change in OH minus. Remember that the H plus concentration would be 10 to the minus pH. Well, OH minus concentration will be the same. It's going to be 10 to the minus pOH, and that's going to be 10 to the minus 2.13, which is 0.0074. So let's just pop that in the ice table. In step 4, we're going to take the change we just calculated and use it to calculate the other concentration changes. So BH plus, again, is going to have the same change. It's a 1-to-1 ratio, and they're both products. And the base, because it's a reactant, is going to have a negative of the same change, so that's negative 0.0074. And now we can calculate our equilibrium concentrations of 0.00926, 0.0074, and 0.0074. So then our last step is to use those concentrations to calculate Kb. And so here is our generic equation for Kb. Let's plug our concentrations into that and whip out our calculator, and we get a Kb value of 5.9 times 10 to the minus 4th. This particular problem also asks for the pKb, so we just use the fact that pKb equals the negative log of Kb, and that gives us a pKb value of 3.23. All right, now let's look at how to calculate a pH from a Kb value and an initial concentration. So this is going to be fairly similar to calculating pH given a Ka value and initial concentration, but you will see there are a few small changes. So we start out by making an ice table, and this time we're setting the change in OH minus to plus X instead of the change in H plus. Again, we use stoichiometry to calculate our concentration changes. Then we calculate the equilibrium concentrations, substitute those concentrations into our Kb, solve for X, and again we get the choice of using the quadratic equation when necessary, or the shortcut if possible. Once we have our value for X, we can then calculate our pOH, and then use the relationship between pH and pOH to get the pH value. So let's try that on a problem. Again, we start off by making an ice table and setting the change in OH minus to plus X. So let's start off by plugging in our initial concentrations, 0.38 in the case of our base, which is ammonia, and then 0 for our protonated form of the base, the conjugate acid, and OH minus. And we're going to put in our change of plus X for the OH minus concentration. Now we use the stoichiometry to calculate the other concentration changes. So again, we're going to have plus X and minus X for the protonated base and the deprotonated base respectively. Now we're going to calculate the equilibrium concentrations. And we're just going to add the initial concentration and the change to get those values. Step 4 is to substitute equilibrium concentrations into the Kb expression. Now, before we do that, we know we're going to have to solve for x eventually, and we'd rather use the shortcut. So I think, given a fairly small value for Kb, that we can use the approximation that 0.38 minus x is about 0.38. And we'll check that at the end. So our Kb is BH plus times OH minus over B. We plug in x for our BH plus and OH minus, 0.38 for B concentration, and then remember that that is equal to 1.8 times 10 to the minus fifth. So now that we have that equation, we can solve for x. So x squared over 0.38 equals 1.8 times 10 to the minus fifth. Multiply both sides by 0.38. And then x squared is going to be 6.84 times 10 to the minus sixth. We take the square root and get that x equals 2.6 times 10 to the minus 3. So now we're going to use our x value to calculate pOH. And since that comes from the OH minus values, let's calculate the final equilibrium concentrations for OH minus. So that concentration and the concentration of our protonated base are both going to be 2.6 times 10 to the minus third. And technically that's the only concentration we need to know, but let's solve for our equilibrium concentration of base because we made an assumption to take our shortcut, and we need to see if that assumption is correct. So 0.38 minus 2.6 times 10 to the minus third is 0.3774, which, if you round to the correct number of sig figs, is 0.38, and so that was a good assumption. So we know that we could use the shortcut values, and now we can calculate our pOH, feeling safe that our OH minus concentration is actually 2.6 times 10 to the minus third. So it's going to be the negative log of that concentration, which gives us 2.58 for our pOH. But the problem doesn't ask for our pOH, it asks for our pH. And so now we need to go on to step 7, where we use the relationship pH plus pOH equals 14. Now I've rearranged that to solve for pH. So let's plug in our pOH value and run it through the calculator, and we get a pH value of 11.42. Does that make sense? Well, 11.42 is a very basic pH, and so yes, that does make sense. If you have to solve for concentrations or pHs or whatever in a base equilibrium, you can use a very similar method to what you did for acids. And really the difference is knowing where to convert between H plus and OH minus, or pH and pOH. And if you learn to do that, these problems are relatively straightforward. I hope this was helpful, and I'll see you again soon.